All right, we are in chapter 7, 8, 9, and 10, kind of doing an overview here of everything. This is Unit 2, taking a look at our notes here of everything, because it seems kind of easier to kind of draw all of this together instead of like the bits and pieces to kind of piece through it. We will go back through and review each individual concept, but this is just to give us a good oversee of how everything kind of works. So take a look at another example here. Miles per gallon versus speed for a new model automobile is fitted with a least squares regression line. Sorry about that. Wanted to change that. Least squares regression line. The graph of the residuals and some computer outputs for the regression are as follows. So there is the output. So this is a graph of the residuals. All right, this is the residuals. All right, and then here is a computer output. You got to get used to reading these as well. Okay. So, as looking at this stuff, interpret the slope of the regression line in context. All right, so some people have a hard time reading all of this stuff. Now, this is us relating to the residuals, right? It has that E involved with it. This is the coefficient, all right? But taking a look at this, it says the regression equation is right here. I got it. So it says interpret the slope. I don't even have to think. Right? I have this stuff. It's already taken care of. Like, you just got to understand how to read the data. So as I look at that, it says the slope is this. Right there it is. That's the slope out in front of that. Y equals some number. That's the slope times the speed, right? So there it is. I already have the slope. Don't even have to try hard. It's either there or there. Notice it's the same thing. That's the speed, the coefficient that's with the speed, and the constant is right there. That's giving me my equation. Right? Because the data printout, literally, it said that right there. That's why. Take a look at this. And the closest thing to that is where speed and coefficient match up. That's with the table. Verbally, this means that the miles per gallon drops. Miles per gallon drops by 0.2179 for every mile per hour increase in speed. So as the speed increases, it literally drops 0.2179 miles per gallon. What is the mean predicted MPG at a speed of 30? So the speed is 30, right? Basically, we plug in 30 and there you go. Get your answer. What was the actual MPG at a speed of 30? Well, looking at the picture, it appears that the residual at 30, so, is around 3.5. So here's what you do. Let's take a look at the graph. Right there. At 30, it's up here. Well, and that's why they're saying maybe it's like 3.5, because right here is 30, and right there would be 5. So yeah, I can bite on the 3.5. So it's around 3.5, right? Well, remember, residuals equal observed minus predicted, right? Well, the residual we know the predicted, I don't know what actually happened. So I add that over, and more than likely, it was actually 35.9 was probably the real value there. So the observed or actual speed would have been 35 to 36 miles per hour, right? Is a line the most appropriate model with this data? Is the other thing we look at. Well, the residual plot shows a pattern, a pretty strong pattern in the residuals. This indicates a nonlinear pattern would be more appropriate. So what does now the S equals 7.252 refer to? All right, and that stands for the standard deviation of the residuals. So S equals 7.252. Let me find that right here. S equals, where are we looking here with the data? Trying to find 7.252. And I'm actually not, there we go. What is S equals 7.252? It's right there. Okay, so that is in the data table. So you can see it. What does it refer to? That stands for the standard deviation of the residuals is what that stands for. That is our standard deviation of the residuals. So when you're looking at that, take a look at another example here. The number of youngsters playing Little League Baseball in Ithaca, New York during the years of 2005, 2013 is fitted with a least squares regression line. The graph of the residuals and some of the computer output is here. So there's the residuals. There's the computer output. I am not seeing a pattern with this. And it says that they did a least squares regression line, which is probably just a simple linear regression line. It kind of looks pretty good. And if I look at this, percentages, right? If I'm looking at these percentages, right, R squared, I mean, that's not too shabby there, right? That's pretty close to 100. So, I mean, like, this is looking pretty good. If I was to create my equation from this, does it appear that a line is an appropriate model? Yeah, right? There's no pattern there at all, and that's r squared is pretty close to 99%. So there does not appear to be a pattern when I look at that. The r squared, which stands for the r squared, right? R squared is 99.4, and it's basically almost 100%. And the equation of that line, where years and coefficient cross, is your slope. So that's the slope, all right, of that years plus that, all right. So right where constant and coefficient crosses the y-intercept, so this is what we end up getting. That just should be a hat there because this is the predicted equation, right? That should be a hat there. In context, this means the predicted number of players equals 123.8. Just on, it's where it starts. Whether no one comes, they're predicting that that's what it should be at the first year in 2005, right? But then each year after, it appears that it's going up by 12.6 kids roughly each year. That's what it looks like it's implying. So interpret the slope of the regression line in context of the problem. The slope is 12.6. It shows us that the number of children increases from 12 to 13 players per year, every year from 2005 to 2013. Interpret the y-intercept of the regression line. It basically means about 123.8 tells us the number of students that were playing in that year 2005, which was probably around 124 kids were playing when it started. What is the predicted number of players in 2007? All right, well, if that was what had started in 2005, right, I put in 2 because it was 2 years later that we're looking at, so I'm predicting around 149 kids were there. Plug a 2 in since that is the number of years since 2005. All right, years since 2005. So it would be 2. What was the actual number in 2007? Well, I need to find the residual. I know the predicted value now in 2007, which is 149, but I need to find that residual. So remember, the observed means actual, right? So I got to find out what it is by looking at the graph. And they're saying, let's see, what did I want in 2007? Does it have the, I don't know if we have it there. Nope, that is the speed one, so I went too far back. I believe, yes. Where is it? There we go. So years, that's 2005, 2007. This is up by 5. So it is. So looking at the residual plot, it is by 5. So we are at, there we go. 5 equals observed minus, well, the predicted is 149. So that's why I plugged that in there. I would add that over to figure out that about 154 is what it would be for the observed. What years, if any, did the number of players decrease from the previous year? So I want to know if they decreased. So in this, the y value should always be going up, right? Because it's always adding more people to it. So the predicted equation is saying that, meaning the predicted value should always be going up when we're doing this. So your tip, simply using a calculator to find a regression line is not enough. You must understand where the stuff is coming from as well as the table. You must be able to interpret the slope and intercepts in the context of the problem as well. So, outliers and influential points as well. In a scatter plot, regression outliers are indicated by points falling far away from the overall pattern. All right, that is, a point is an outlier if its residual is an outlier in the set of residuals. All right, so kind of funny to say it that way, but all right, in a scatter plot, regression outliers are indicated by points falling far away from the pattern. That's easy to see, but a point is an outlier if its residual, all right, if its residual is an outlier in the set of residuals. So that's definitely confirming that it is a residual is what it means. If you're looking at your plotted points of residuals and you see one way out there, like point here, here, another point here, here, and then there's one way out there, that's probably an outlier. That's what that means. So for example, a scatter plot of grade point averages versus weekly television times for a group of high school seniors is as follows. Possibly an outlier, possibly an outlier, right? I see a pattern otherwise. They could possibly be outliers depending on it, right? By direct observation, we note that there are probably 2 outliers more than likely. One person watches about 5 hours and gets a 1.5 GPA. That means they barely watch TV, but they still don't do well, we'll just say, in school. One person watches about 15 hours of TV, and gets roughly a 3-ish, which is not too bad. So I guess, sorry, it's supposed to be 25, I believe. It gets roughly a 3. Right, here's around 25, they get a whole way up here around 3. So one person did that, and that's not overly likely either. Also note that while 30 hours of TV may be considered an outlier for the TV hours, just like the 0.5 GPA may also be considered an outlier as well. What they're saying is maybe this is an outlier, or maybe that is an outlier as well. Okay, so they just don't appear to be, because they're also in that regression as well. So those are possibilities. The 0.30, 0.5 may be considered an outlier, but it is not an outlier because it falls within the pattern of the data. Scores whose removal would sharply change the regression line are called influential scores. Meaning, if I took that point away, that's not going to change anything. But if you take one of the outlying points away, that's probably going to be an outlier if it sharply changes how the regression line looks. Okay, those are what make influential points. An influential score may have a small residual, but still have a greater effect on the regression line than scores with possibly larger residuals but average X values. For example, consider the following scatter plot of 6 points in a regression line. All right, so I'm actually going to stop the video right there, and we'll start where we come back because I don't want to get too close to a time window where I have to speed through this. So when we come back, we're going to look at some influential scores is basically where we are at.